One of the odd things that happens in mathematics is that you get relatively good at approximating, especially in the sciences, chemistry, physics, and biology. You get pretty good at getting it almost right. And most of this sort of calculation needs to be done off the cuff with nothing at hand but your head. So, a legitimate question. What's the square root of 27? No calculators, no phones, nothing. What's the square root of 27? 5 point something, right? A little bit bigger. How could I get that more precisely? Well, let me think about derivatives and tangent lines. I know, it's a weird idea to jump from square roots to that idea. But if I think about the graph of the square root of x, I know that at 25, we're at 5. So what if, instead of trying to figure out the square root of 27, I instead drew a tangent line? So let's take the tangent line at 5. Given the scale I've got on the x-axis, 27 is only a little bit to the right. That's 25. 27 shouldn't be that much further over, right? And that means the y value for 27 is going to be right about there. Can you tell me whether I drew that dot on the curve of the square root of x or on the tangent line? Those values are really close together, aren't they? So what if I actually used the equation for the tangent line to figure out the square root of 27? Well, it wouldn't be figuring it out, it'd be approximating it. Aha, I'd use a straight line to approximate my value. I like this idea. Okay. How do I find the equation of that tangent line? This is a question you should be able to answer. How do I find the equation of a line? Yeah. Okay, when I differentiate, what's that going to give me? The slope of that line. So I take y prime, and if I rewrite this as x to the 1/2, then I can use the power rule, or 1 over 2 square root x. I have the slope by plugging in 25. Square root of 25 is 5. So that is 1/10 or 0.1. I'm almost there. What is the actual equation for the line? That's my slope. What else do I need? The point. But the point in question has a equal to 25. That's this dot right here. And we know the y value that goes with that. And now I can go to the point slope form of a line. Y minus y0 equals mx minus x0. I just put in the y and the x from the point we got, 25.5. I'm not even going to multiply any of this out. All I'm going to do is move the 5 from the left side to the right side. And I have y equals 5 plus 0.1 x minus 25. So if I ask you to approximate the square root of 27, instead of trying to figure out what I'm going to get when I plug it in here, I can figure out what I'm going to get when I plug 27 into this equation. This equation is called the linear approximation for the function we are using at the value we chose. Based on this, if I asked for the square root of 27, I'd say, well, that's approximately the value I get when I plug 27 into this. How far off am I? Grab your calculators. What's the square root of 27? I am off by less than 0.01. Actually, let's do the subtraction. Minus 5.2. It's a little itty bitty number, isn't it? That is 0.07%. That's pretty damn good. Less than 0.1% off with an approximation. Square root of 24, square root of 23, same idea, right? As long as I'm working on a number near 25, I'm good to go. Now, I did put near in quotes here on purpose because how close is close enough for 25? If I asked for the square root of 35, would this work well? Why not? Closer to another perfect square, 36. square root of 17, and 17 is closer to 16, a different perfect square. But as long as I'm asking for a number near a perfect square, then the curve and the line are sufficiently close together. I can do this for any function, as long as f is differentiable. So let's generalize this. Let's suppose I have any function, and that function is differentiable in some interval containing the x equals a. That's the point I'm going to use. Ideally, that's a value of x where I know the output. Like I used 25 because I knew the square root of 25. If I want an approximate value for f of x, where x is near a, I'm going to find my tangent line. So I have this point, a, f of a, and I've got some other value x, and instead of getting this dot, I'm going to get that dot. Instead of getting the dot for f of x, I'm going to get the dot on the line. I'm going to give this line a name. I'm going to call this L sub f of x, the line for f. Aline, I'm going to go through exactly the process you told me to. I'm going to take the derivative. Actually, I'm just going to plug in a rather than just find the general derivative, right? I'll find f prime of a. That's the slope. So then I will have y minus the y value at a equals slope times x minus a. And if I move this number from the left side to the right side, I'll have the same equation that we did here. This is my linear approximation formula. It works for any differentiable function. As long as I know that we're not too far away from a. The bigger this value gets, the bigger x minus a gets, the worse this approximation becomes. So here's the graph of the square root of x. And there's my 0.255. If I graph the line we came up with, 5 plus 0.1 x minus 25, there's my tangent line. Now this actually allows me to see why, as I get closer and closer to 36, the graph and the line start to separate again, don't they? And if I come this way and I get further away from 25 to the left, again, the graph and the line separate. But in this section around 25, they're really damn close. They're almost indistinguishable in this picture. So with this same idea, I could ask, what's the cube root of 1700? Now, why the hell would I want to do that? That's a question I get asked frequently. I pulled this number out of thin air, but I have been asked to take cube roots frequently. This is an engine displacement. I've got a 1700 cubic centimeter engine. How big is it? How physically big is the engine compartment? I need to know the cube root of the displacement. I don't work on vehicles all that often, but this is the total piston head area. 1700 cc's is a small engine. Maybe it's a lawnmower. Small motorcycle? Who knows? But now I need to know a number whose cube is near 1700. And it turns out there's actually a really nice number whose cube is near 1700. 12 cubed is 1728. And then I'll be able to figure out what this answer is. So let's walk through the same process. If this is my function, I need its derivative. F prime of x, y prime is say that again? 1/3 of x. Negative 2/3. Perfect. Now, I'm going to write that with the x to the 2/3 on the bottom. And I'm going to write that as a cube root squared. Right? Because a 2/3, the third becomes the cube root. I put the square on the outside, not the inside. I put it in either place. I promise there's a reason for that. Because what I want to do is I want to plug in 1728. What's the cube root of 1728? So that's what's going to go here, squared. And 12 times 12 is 144. Do the multiplication. 4 times 3 is 2, carry a 1. 4 times 3 is 2, carry the 1. 1 times 3 is 3, with the 1 carried, 1 over 432. But now I can plug in my numbers to the equation I want, because I know f of 1728 is 12. That's our cube root. I have my linear approximation is f of a plus f prime of a, x minus a. That's 12 plus 1 over 432 x minus 1728. Now I can plug in the number I know. The approximation for 1700 is 12 plus 1 over 432. 1700 minus 1728, that's negative 28. This number is going to be smaller than 12. I'm pretty sure this fraction is not going to reduce nicely. If I grab my calculator at this point, I get 11.935. All right, you've got a calculator. What's cube root of 1700? Hot damn. That's really close. Questions? The one I get asked the most is, so what? What good is this? Let's do this again. Here's the function I want you to use, sine of x. And I want you to use it near the point where x is 0, at a equals 0. I really like this one. What happens when you work out your linear approximation here? I just get y equals x. Because my derivative, root of sine is cosine. Cosine of 0 is 1. Sine of 0 is 0. So my linear approximation is f of x plus f prime of x, x minus a. That's just x. In other words, When x is near 0, sine of x is roughly the same as x. Now, I can actually claim that I already knew that. Why do I claim I already knew that? It's because way back in chapter 2, when we first started talking about limits, we took the limit of sine x divided by x, didn't we? And we got 1. Sine x over x is roughly 1, then sine x is roughly the same as x. If I graph these, from here to here, it looks like those are exactly the same, doesn't it? Why in God's earth would I need this piece of information? Snell's law tells me how light bends as it goes from one medium to another. That's the way glasses work. It bends the light. But it bends it according to the angle made between the two surfaces. So I have the light coming in, hitting the glass. It bends in the glass. It changes angle from theta 1 to theta 2. There's some coefficient called the index of refraction. By default, in air, we use 1. Which means if I can measure the bend in this angle, well, the bend in the sine of the angle, right? I can figure out N2. N2 is equal to sine theta 1 over sine theta 2 because N1 is 1. But this tells me that when those angles are small, that's the same as the ratio of the angles themselves. I don't have to do anything with trig functions. This is called first order because we created a linear equation, degree 1, first order optics. And first order optics are how spectacles were developed. And the reason I can use different glass to make different angles. And Ben Franklin in the 1700s decided to put 2 different pieces of glass on the same thing, creating a bifocal. If you wear corrective lenses at all, this is why they work. Until the advent of computer-controlled lens design, which is the 1970s, this was the way they built your glasses. Up until my lifetime, this was the best way to do lens design. Questions? Calculation of index of refraction is really straightforward when you're using small angles. You just have to measure the angles precisely. And you have to measure them in radians. I could ask, for what range of theta is this approximation closer than, I don't know, how about 0.05? This is an epsilon delta idea. How close do I have to get to be close enough? And in this case, close enough is 0.05. So I really want to know where sine of x minus the linear approximation of x is less than 0.05. But I can calculate that directly. What I'm going to do is I'm going to graph not these two functions, but their difference. And then I'm going to graph the epsilon and delta line at 0.05 and minus 0.05. And I'll see where we cross. Now, my window right now is set up to go from minus pi to pi. But my y values are way too big if I'm looking at 0.05. So let's make this a lot smaller. Now my lines should be visible in the middle of the screen. It's going to start with the trig function. That's sine of x minus x. Oh, there you go. As long as you're between this theta value and this theta value, you're less than 0.05 off from sine of theta. Find me one of those two values. This is where you should all have calculators out doing this thing. The one on the left is negative 0.674 radians. The one on the right is positive 0.674 radians. 0.67 radians doesn't mean jack to me. How many degrees is that? How do I convert that to degrees? There's a little bit more to it than just multiplying by 180, but multiplying by 180 is definitely part of it. I have to multiply by 180, but 180 degrees is how many radians? It's pi radians. So I have to divide this by pi. Are wait a minute, wait. 38 degrees? You're telling me that if my angle is anything less than 38 degrees, above or below, that's a 70-degree field of view. That's why even badly made glasses from 400 years ago still work. Because as long as you're looking out in front of you, you'll still be able to see perfectly. That's pretty damn good. Questions? There are lots and lots and lots of places where a first order approximation is good enough. We do this a lot, filling in values in tables. In a lot of classes, it's easier to work with table data. This is from a statistics class as an example. But it might be to my benefit to try and find a value. Let me use this one instead. If I want to know what z value gives me 0.05 exactly, well, I have a problem because 0.05 isn't available in the lists of things that come up. I go between 0.0478 and 0.517. 0.05 isn't on here. So I'd have to split the difference here, right? Should it be exactly in the middle between 0.012 and 013? So should it be 0.0125? Well, it's a little further to this side than it is to this side. The difference from 0.05 to 0.478 is more than the difference this way. It's 22 points this way. It's only 17 points that way. So maybe I should be a little further one way than the other. We can draw the straight line between those two and find the right x value. This is called linear interpolation. It's how signal conversion gets done. When you convert from one encoding to another, say in an audio file or a video file, when you do compression, you interpolate it between values. That's a straight line behavior. It's the same kind of line. Okay, wait a second. I had my linear approximation formula. And when I think about the picture we were looking at, I've exaggerated the picture. I've blown it up quite a bit. So I'm going to say that here is our A value and way over here is our X value. Right? When we do the linear approximation, we get this value. That's roughly, right triangle again, that's a change in Y, isn't it? The change in Y is roughly the change in X times the derivative. Wait a minute. This is slope. Isn't slope change in Y over change in X? Change in Y. This is just treating them separately. Like the change in Y and the change in X are separate bits. I like that idea. I want to stick with that idea. I'm going to call this, instead of delta Y and delta X, I'm going to use my derivative notation, dy dx, right? If I use that up here, then I get dy is approximately equal to f prime of x dx. We're going to call these two pieces differentials. And I can treat them separately as opposed to just treating them as part of dy dx. Like the numerator and denominator of that fraction are really separate ideas. And I'm taking the ratio. By the way, in the history of calculus, this was a really complicated idea. There's a lot of debate that goes back and forth about how to treat these differentials, especially when they get really small. when they're fairly large ideas, it makes sense. And this expression here is really our linear approximation. Let me go back to the way we wrote the approximation up here. Not this line, this line. Change in y, slope, change in x. That's this equation, isn't it? Change in y is equal to the slope times change of x. Encoding this like this allows me to use these two ideas separately. We were dealing with the square root. What was the derivative of the square root? So I could write dy equals 1 over 2 root x dx. And separate my two differentials. Wait a minute. Wait a minute here. Chain rule, right? What I did is I said, let's think of this as e to the ugly. Yes? If I write dy here, what's the derivative of e to the u? So I'd end up with this, wouldn't I? But in order for this to be true, I needed to be using those two things as equal, right? Yes? So if I say, oh, but in this case, u is equal to sine of x, then what's du? It's the derivative of sine of x. And if I swap that right up into here, I get dy is e to the u du. And if I put that back over there, there's my chain rule. The derivative of the inside is really rearranging my differentials. Oh, I like this linear approximation idea. This frees me up from so many different things. Propagation of error. Okay, lab science time. If I take out my measurement and I measure the radius of a sphere and I get 21 centimeters, my ruler has centimeter marks and it has millimeter marks, right? Do you have a ruler that has tenth of millimeter marks? Me neither. Which means I could be off by half a millimeter on either direction, couldn't I? I could be over by half a millimeter and have rounded down to 21, or I could be under by half a millimeter and rounded down. Really, if I write 21.0, then I've got a give or take of 0.05. because I'm rounding to the nearest millimeter. This is the error in my measurement. But now I ask you, what's the volume of this sphere? How do you compute the volume of the sphere? It's 4/3, not 3/4, and it's cubed. Because it's volume, it's cubic units. So hang on a second. I have a possible error here. If I use this calculation, I could be off, right? So let's think of this measurement error as a possible change in R. How much could my volume be off by? Write out differentials. Take this and tell me what's dV. I'm good with that, 4 pi r squared, but there's one other thing there, Jack. dr. You just said where I take the r as u, right? Then I need the derivative piece, don't I? This over here, this looks just like our related rates, doesn't it? The only thing that's missing is the dt's. This is the same idea as our related rates. But this would tell me if you know how much your radius changes, you can tell me how much the volume would change. So if I use r equals 21 and dr equals 0.05, then dV is 4 pi times 21 squared times 0.05. What do you get? Oh, 09? No. All right, well then let's just go 277.1. And that is cubic centimeters, isn't it? Centimeters here, squared, and another centimeters. That's cubic centimeters. 277 cubic centimeters, give or take in either direction. If this is water, it's 250 milliliters of water, right? 8 ounces. It's a cup of water. Maybe this is more valuable liquid or gas or whatever. I don't know what you're filling this balloon with, this sphere. But 277 possible cubic centimeters in either direction might be a matter of error that is important. I can do relative error, I can do percent error, right? Relative error would look like this. Relative to the thing it is the differential of. I can even compute this with the formulas before plugging in numbers. dV over V is 4 pi r squared dr over 4/3 pi r cubed. Cancel the pi's, cancel the 4's, flip this fraction up, and I get 3 dr over r. Relative error and propagation of error. When you have an error in a measurement, then you use that in a calculation, you move your error down the line. If you don't account for that, that can throw off your results in any lab you're doing. by substantial factors. In this case, though, this actual propagated error is very small. It's only about 0.007% error, 0.7%. I am absolutely positive that those of you going forward in lab science courses will use this stuff if you haven't already. I will see you all on Monday. Have a wonderful weekend.